Alright, so this is the test 2 review. Feel free to pause at any time, try to solve it yourself, or if I'm moving too fast, just pause it and catch up, and yeah, hope this helps. Alright, so this question asks, in the following chemical reaction, the oxidizing agent is, so keyword in this question is agent, so this is not the element that is being oxidized, this is the element that is doing the oxidizing, because in a redox reaction, first something has to oxidize so that it can lose the electrons, and then something is reduced and it gains those electrons that were lost. So we'll start by assigning charges. Alright, so first we have hydrogen peroxide, which in this case oxygen does not have a charge of -2. This is the exception, so we'll have a +1 and a -1. Next, permanganate, so we'll have -2 times 4 would be -8, but we want to end up with one negative charge, so this will be a +7. This is +6. Again, anything that is an ion with a charge, that will automatically be its charge. And then we've got water, so we've got -2 and +1. And then this is a free element, so this is a charge of 0. So if we look at the element that's being oxidized, we'll notice that oxygen here has a -1 charge, and here it has a charge of 0. So for our oxidation part of the reaction, we're going to have hydrogen peroxide to just oxygen. Then for the reduction portion, we will have permanganate to just a manganese ion. So the manganese is going from a +7 charge to a +2, so it's being reduced and it's gaining electrons. So from here we could deduce that our oxidizing agent is permanganate, because it is the one that is taking the electrons. But I'll go ahead and work this the rest of the way out just so you can see it. So here we want to even out both sides of our equation, so we'll add 2 hydrogens, which adds 2 positive charges. So now we have a +2 charge here, and we have a 0 on this side. So we will add 2 electrons to cancel out that charge. So now, for our permanganate, we've got 4 oxygens on this side. Our manganese is fine, but we've got 4 oxygens on this side. So we'll add 4 waters to get our 4 oxygens, but that leaves us with 8 hydrogens. So we'll add 8 hydrogens to this side. This leaves us with a total of a +7 because we've got 8 H+, and then this negative charge from the permanganate. And then over here, we've got a +2 charge from the manganese. So we need to add 5 electrons to this side. And then to even these out, we can multiply all this by 5 and all of this by 2. So that will leave us with 5, 5, 10, 10. And this will be 10, 16, 2, 2, and 8. So now we can just look at each side and get rid of any duplicates. So here we've got 10 hydrogens, that means we can take this down to 6. And that leaves us with this balanced reaction. So in that way we can check ourselves and make sure that we were indeed right in identifying the oxidizing agent, which is permanganate. Alright, so this question is asking for the reducing agent. Again, this will be the one that is causing the other one to be reduced. It is not the one that is being reduced. Keyword is agent. So just like the last question, we'll assign charges. Feel free to pause and do it yourself, and you can check. So alright, so now we've got all our charges. From a quick glance, we can see that iron is losing some electrons, or 1 electron, and in this one, manganese is gaining 5 electrons. So we are going to write this out, showing first which one is losing the electrons. So we've got Fe2 plus goes to Fe3 plus. And then for the reduction portion, we've got permanganate goes to manganese. This would make Fe2 plus our reducing agent, but I'll go ahead and work it the rest of the way out just so you can see it. So over here we've got an even number of iron on both sides. We just need to balance out the charges. So we've got +2 here, +3 here. We can fix that by adding an electron. Use electrons to balance charges. So now we'll move on to the permanganate. So we've got enough manganese on both sides. We've got 4 oxygens on this side, so we will add 4 waters for our oxygen. That leaves us with 8 hydrogens that we need to add to the other side. So it's very similar to the last question. So we've got a +7 on this side, +2, add 5 electrons. So now here in this question, all we have to do is multiply all of this by 5 to even out the number of electrons. So that will give us our balanced reaction that we see here. Alright, so this is another redox reaction. So we'll start by assigning charges. Go ahead and pause and do that, and then you can check yourself. Next, we'll identify which one is losing electrons. Here it looks like carbon. So we've got C2H4 to CO2. And oxygen is gaining some electrons. So we've got oxygen, and that turns to water. So now we can start to balance this equation. So we've got 2 oxygens on this side. We've got 2 carbons on this side and only 1 on this side. So we're going to double this here. So now we've got 4 oxygens on this side. So we'll have to add 4 waters. Well, now we added all that water, and we've got to add some hydrogen to balance it out. So here we've got 8 plus 4, so we need 12 hydrogens. And now we've got a +12 charge here, 0 over here. So we will add 12 electrons to balance the charges. Down here we've got 2 oxygens here, 1 water here. So we can add a 2 here to balance out that oxygen. And then we've got 4 hydrogens here, so we'll add 4 hydrogens here. Now we've got a 0 charge on this side, +4 here, so we'll add 4 electrons. Now to even out these electrons, we've got 4 here, 12 here. 12 divided by 4 is 3, so we can multiply by 3. 12 electrons, 12 hydrogens, 3 oxygens, and 6 water. Now we can cancel out anything extra, so we've got 12 electrons on this side, get rid of that. We've got 12 hydrogens here, 12 here, and we've got 4 waters here and 6 here, so we can subtract those and we will get 2. So that leaves our coefficients 1, 3, 2, and 2. So the answer will be 3. Alright, so I don't want this video to be too long, so I'm just going to, for the rest of these redox questions, I'm just going to write in the answers, and then you can pause the video and look at it and see if you worked it out properly. Alright, so we can actually work this question out without doing an entire redox reaction. So we've got, first I would just start with the most obvious ones. We've got 4 fluorines here, and we've only got 1 here. So we'll add a 4 here. That leaves us with 6 hydrogens on this side. We've got 2 here plus 4, and then we've only got 2 here. So we will multiply this by 3, and now we've got 6 hydrogens. We've got 3 oxygens here, we've got 3 oxygens here, we've got 4 fluorines, we've got 4 fluorines, we've got 1 sulfur, and we've got 1 sulfur. We're good. We add all these together, the answer is 9. Alright, so this is question 19 on the practice exam and also question 3 on the worksheet. So this question says that copper metal has a specific heat of 0.385 joules per grams times degree Celsius. Wants us to calculate the amount of heat required to raise the temperature of 22.8 grams of copper from 20 degrees Celsius to 875 degrees Celsius. So the key to these questions is going to be knowing which equations to use for which questions, because you will have all of the equations provided to you, but you'll have to know which ones to use. So since this one is asking us to calculate an amount of heat to change temperature, we're going to pick this equation. And then you can just fill in all these numbers, and Q will equal 22.8 grams times 0.385 joules per grams times degrees Celsius. And then this will be times so this is final temperature minus initial. So in this case, this is our final and this is our initial. So this will be 875 degrees Celsius minus 20 degrees Celsius. If you multiply all that out, you will get 7,505 joules. And if you divide this by 1,000, or you can look at it as dimensional analysis, we will get 7.51 kilojoules. Alright, so for this question, we're going to use the same formula. So if we just fill in these numbers, it says the water loses 11.7 kilojoules. So first thing I would do is just convert that to joules. So that's going to be 11,700 joules. Secondly, it loses. So this value is actually going to be negative. So we've got negative 11,700 joules because the system or water is losing heat. So now we'll include our mass times the specific heat, and we're looking for a final temperature. So we don't know final temperature, but we do know that we start at 20 degrees Celsius. So if we divide Q by M and S, so we'll get 200 grams. And alright, so now what we have is negative 13.98 degrees Celsius equals final temperature minus 20 degrees Celsius. So all we have to do is add 20 degrees Celsius to both sides, and our answer will be 6 degrees Celsius. Okay, so this is about a combustion reaction, so we're going to be using thermochemistry. So based on all these, this equation, the H of reaction is equal to the sum of moles times standard enthalpy of formation of products minus the sum of the moles times enthalpy of formation of reactants. So if we just plug in all these numbers, we get negative 11,020 is equal to 16 times negative 393.5 plus 18 times negative 285.8 minus 2 times the number we don't know, the enthalpy of formation of octane. So let's go ahead and solve this part. So 16 times negative 393.5 is going to be 6,296, and then this will be negative 5,144. If we add those numbers together, we'll get negative 11,440. So we've got negative 11,020 is equal to negative 11,440 minus 2 times the enthalpy of formation of octane. So we can just add 11,440 to both sides. That will give us 420 is equal to negative 2 times the enthalpy of formation of octane. And now, if we just divide 420 by negative 2, our answer will be negative 210 kilojoules per mole. It can't be any other unit because those are the only units we used. Alright, so this one is also number 8 on the worksheet. Asks how many grams of graphite must be burned to release 275 kilojoules of heat. So we want 275 kilojoules, so we'll start with what we supposedly have. We'll convert this into moles. Why? Well, there's no other value here. So 1 mole is negative 393, but we can't have negative grams, so we'll just do 393 kilojoules. That'll get rid of this unit. Now we're here with a mole, but we want grams. How do we get from moles to grams? We use our molar mass. So molar mass of carbon is 12.011 grams per mole. If we multiply this out, we will get 8.40 grams. And you can use that format for every question like this. Just go from kilojoules to moles to grams. Alright, so this question is just going in the opposite direction. So we're going to go from kilojoules to moles to grams if we want to find grams in the end. But if we're starting with grams, then we just need to reverse it. So moles to kilojoules. So we start with what we have, 35.0 grams, times the molar mass, 46.1 grams, and 1 mole, times this other number we have, 1 mole for every 1,367 kilojoules. So we'll cross out all our units, multiply this, and you get 1,040 kilojoules. I mean, I got 1,038, but, close enough. Alright, so now there's some Chapter 4 questions. This one is a limiting reagent problem. So, we've got 22 grams of sodium chloride and 21 grams of sulfuric acid. So we're going to mix them up and we're going to react them. But one of them is going to run out first. And whenever one of them runs out, the reaction can't continue. So we're going to figure out at what point the reaction is going to stop. So, which one of these is going to run out first? So, we will take our 22 grams of sodium chloride, and we are provided absolutely nothing else. So, what I would suggest is that you just use your molar mass at this point. And since our only other information is this equation, we're going to have to relate this mass to our equation. And the only way we can do that is using moles. So we will take our 1 mole of sodium chloride, which is 58.44 grams. Now we can look at our equation. We've got 2 moles of sodium chloride for every 1 mole of sodium sulfate. And you may say, why are you picking that one? Why not this one? Well, you can do either one. You just have to use the same one for both of these reactants. But either way, you will get the same answer, at least as far as which one would run out first. So we've got 2 moles of sodium chloride, 1 mole of bisodium sulfate, and this will equal 0.188 for the bisodium sulfate. If you were to do this same equation using the hydrochloric acid, you would get 0.376. So now we're going to use our sulfuric acid. Again, we'll use our molar mass, which is 98.1 grams. Then we'll use our molar ratio. So we've got 1 mole of sulfuric acid for every 1 mole of bisodium sulfate. So that gives us 0.214 or 0.428 if you use hydrochloric acid. And you can see that in either case, this number is larger and this number is smaller. So that means that without a doubt, sodium chloride is our limiting reagent. Alright, so this question asks us to take it a step further and determine how many grams of a product we can derive from this reaction with this certain amount of our reactants. So in this case, you would have to use this product in your equation. So we'll start with 16 grams molar mass and then we'll do our molar ratio. So this is a 1-to-1. And then, so now we've got moles of chloride, right? So we've gotten rid of grams here, we've gotten rid of these moles, and now we're at moles of chloride, but we want grams of chloride. So now we're going to have to use the molar mass of chloride. So 1 mole of Cl2 is 70.9 grams of Cl2. So that's 2 times 35.45 from the periodic table. And that will give us 13.1 grams of Cl2. So we'll just do the exact same thing with the other one. And that will give us 14.6 grams of Cl2. So what does that mean? What's our answer? So how many grams of Cl2 can be prepared? Well, really, we can only make this much because once this reactant runs out, we can't make any more. So we can't actually make this much because we don't have enough of this reactant. So our answer will be 13 point, well, on the test it's 0, but close enough. So this one is asking for the mass of excess reagent remaining at the end of the reaction. So here they're saying, okay, we mix these two things together. One of them ran out, and we've now got our product, but we've also got a little bit of reactant left. And so they want to know what the mass of that reactant that still remains. So first we'll figure out which one is going to run out first. So we've got 90 grams of SO2, so we will multiply that by molar mass, and then we will use our molar ratio, so this is a 2-to-2, and then we can just stop there because since this is the same product, we can just compare it in moles. So now if we do the same thing with 100 grams of oxygen, molar mass of O2, 16 times 2, then use our molar ratio. We've just got 1 mole of oxygen here. And then we get 6.25 moles of SO3. So this one runs out first, right? So what we need to know is if we made 1.4 moles of this product, how much oxygen would we use and how much would we have left? So if we have 1.4 moles of SO3, we can use our molar ratio here. We're just kind of working this backwards. And now we're getting back to our grams. So we're just basically doing this backwards so that we can get back to the answer that we want, which is how many grams of oxygen did we use if we just make this much instead of this much. So now mole of oxygen. So now we've got the unit we want, right? And so we've got 22.4 grams that we used. But we started out with 100, and we want to know what the excess is. So we need to subtract 22.4 grams, and that will give us roughly 77.5 grams, if you include all your decimal places. And now I'm going to do just a few of the worksheet chapter 5 problems. So this question starts with 115 grams of ethanol at 18.2 degrees Celsius. And they're asking if it absorbs 1,125 joules of heat, what will be the final temperature? So we've got heat, we've got change in temperature, so we'll use this Q equals M times S times temperature final minus temperature initial. So we can plug in all these numbers, and we're saying that we've absorbed, so it'll be positive 1,125 joules. We didn't lose heat, we gained it. So, and this equals to 115 grams times 2.46 joules divided by grams times degrees Celsius times temperature final, we don't know what that is yet, minus this 18.2 degrees Celsius that is our temperature initial. So if we multiply these two numbers together and then divide this number by those, we get 4 degrees Celsius. And then that would be equal to temperature final minus 18.2 degrees Celsius. So all we have to do now is add 18.2 degrees Celsius, and we will get our final temperature as 22.2 degrees Celsius. Alright, so this question is a little bit more complex. So we've got 0.7521 grams of benzoic acid. It was burned in a calorimeter containing 1,000 grams of water. The temperature rose 3.6 degrees, and we want to know the heat capacity. So that's C. Other word that we've got in here is bomb, right? So that's going to give us our key to figuring out which equations we're going to need. So first, we will need to know this one. Q reaction is equal to negative Q water plus Q bomb. So the other equation that we're going to use, we get from needing this C, right? So we're going to use Q reaction, right? We'll get Q reaction here, and now we can use it over here to find C times delta T. And delta T for us is going to be positive 3.60 because that's what our change in temperature was. It rose 3.6 degrees. So first thing that we need to do is figure out Q bomb. And we'll just do that one first because it's a little bit faster. So what we're going to do is take this amount of 0.7521 grams benzoic acid. And they've just given us this heat of combustion, so we can just immediately figure out how much energy that's going to produce. So that saves us another step, so that's negative 26.42 kilojoules divided by grams. And that will give us our Q bomb of negative 19.9 kilojoules. Now for Q water, we'll use one of the equations that we've been using pretty frequently before, which is going to be this M times the specific heat times delta T, and the specific heat of water will be provided to you. So first we'll do our mass of 1,000 grams, and we will multiply that times the specific heat, which is 4.184 joules, divided by grams times degrees Celsius, and then we'll multiply that by the temperature change of 3.0 degrees Celsius, get rid of these, and so then our Q water will be, it'll come out in joules, so then just divide by 1,000. 1,000, okay, nope. Can't fit it there. Divide by 1,000 to get from joules to kilojoules, and you will get 15.1 kilojoules. So now we can finally plug this into this equation here to get our heat capacity. Well, no. We can get our Q reaction, so then we can plug that in here and get our heat capacity. Man, okay. Anyways. So, Q reaction will equal negative 15.1 kilojoules plus negative 19.9 kilojoules. That gives us a Q reaction of 4.81 kilojoules, and that will come out to a positive. This will be a negative value, and then if you multiply this here, you'll get a positive value. So now we can plug this into this reaction. So this is going to equal C times our change in temperature, which is 3.6 degrees Celsius, and that will give us our, if we divide this by 3.60 degrees Celsius, so that we can get rid of this, our heat capacity will be 1.34 kilojoules per degree Celsius. Alright, so in this question we're asked for the standard enthalpy change. When it's given to you in this format where you're given multiple equations like this, so we've got this one equation and we don't have an equivalent here, so we're going to put these two equations together and try to manipulate them in a way so that we end up with this reaction that we want. And by doing that, we can calculate the delta H value by relating these two equations and thereby relating these two values. So we need to somehow mess with these two equations at the bottom so that they turn out like this top equation. So what we're going to do is figure out what's good, what's where we want it, what's what we want to keep. So this is great here, right? That's exactly where we want it. We want to keep that there. Right here, we've got 18 water, and we've got 18 water. So this equation's looking pretty good. So now I don't see anything else that's exactly the same, so I'll start looking at what's next close. So right here, I've got 17 moles of oxygen. Here, I've got 25. So I know that I want to somehow lose 8. And if you need to keep track of it on the side, you can do that. So next, I've got the only thing left I've got is my 16 carbon monoxides. Now, so that means I definitely need to just get rid of this, right? I need to lose 16 carbon dioxides, right, for equation 1. And then for equation 2, see, I've got my carbon monoxide here. That's great. So, but it's on the wrong side, right? So, what I'm going to do here is just reverse this equation. Whatever you do to this equation, you have to also do to this delta H value. So, if I flip this reaction and make it into this, that means that I need to reverse the sign of this delta H value. Now I've got 2 carbon monoxides here. I've got 16 here, and then again here I've got 16 carbon dioxides, and I can cancel them out with these, but I need more. Well, luckily those two values fit up perfectly, And what else is we need to lose these 8 oxygens. Well, that's great. If we just multiply everything by 8, then we'll end up with this. And if we just balance it with this other equation here, so this is going to be equation 1. And we'll just balance this like we did with the redox reaction. So we've got 16 here, 16 here, and get rid of that. We've got 8 here, so we'll just subtract 8, and that will give us, if we add those together now, we'll get exactly the reaction we wanted. But now we need to figure out the standard enthalpy change. So along with multiplying this equation by 8, we also need to multiply this now positive value by 8. So if we multiply that out, we'll get 4,528. So now I just need to add these two together. So if I add 4,528 to negative 11,020, my answer would be that the delta H value for this reaction is going to be negative 6,492 kilojoules per mole. Alright, so this one is similar to the last question, except that here we've got 3 equations, and we don't have an included equation. I think it must have just been an error for the actual formation of methanol, so I will just write that in. So we just need to manipulate these equations here to get to this equation here. So first we'll start with what we have and we want to keep. So here I see I've got my graphite taken care of. That's great. I've got an oxygen here and I've got oxygen here, but I've got too much oxygen. So I need to do something with oxygen, right? So next I've got carbon dioxide here, and I don't have any carbon dioxide here, so that's going to have to go too. So this is for equation 1. For equation 2, let's see. So we've got an H2 here. We need more H2. And let's see. Oh, we've got some more oxygen here. So we can worry about that later. That looks like it's exactly what we want, but now we've got too much oxygen somewhere else, but we'll worry about that in a minute. So now we've got water over here. We have no water, so we need to worry about water now. For third equation, okay, so now we finally got our methanol, right? But it's on the wrong side, so that should be the first thing we take care of. So we will take that whole equation and just flip it around. I'm just going to leave out the states just to make it less crowded. And then we'll make sure to reverse the sign of this value. So now if we look at the amount, we've got 1 mole, we've got 1 mole. Okay, great. And you'll find that once you get to this point where you manipulate the final equation and get your final product to where it needs to be, everything else just kind of falls into place, because now here I've got carbon dioxide on opposite sides, so that takes care of this problem. So now I'm going to look at what I need more of. So right now I need more hydrogen. That's my next biggest problem. So here in my equation, I've got 2 moles, but here I've only got 1. So that means I need to multiply this entire equation by 2 and do the same thing to this value. So that takes care of this problem. So now I've got 2, I've got 2 times a half makes 1 whole, and I've got 2 waters. Okay, well, here, first thing, I'll get rid of my water here. I didn't want that anyways. So that takes care of that problem. So now I've just got oxygen to contend with. So here in my equation, I want 1/2 of the oxygen on the left side of the equation. So if I look at what I've got here, I've got 1 mole of oxygen there. I've got 1 mole of oxygen right here. And then I've also got, from this equation, so this is this equation that I just rotated, I've got 3 halves of an oxygen. So if I do 2 minus 1.5, I will end up with 0.5 or 1/2, which will give me this 1/2 mole of oxygen. So now that I've manipulated all these values, I can just add all of these together to get my final answer. So negative 393.5 kilojoules minus 571.6 plus 726.4, and your answer should be negative 238.7 kilojoules per mole. Anyways, I hope that video was helpful. If you guys have any other questions, just let me know. Good luck.